thank you very much, Joe, for the kind introduction, and I would like to start by thanking the awards committee for selecting me for this award. It's a great honor, and I really feel at home in the Canadian statistics community, so I really deeply appreciate that. And I will start with the most important slide of this talk, which is thanking the many great people whom I encountered on the way to getting here, because for sure, without all of them, this wouldn't have been nearly as fun and nearly as productive. So of course, my first and biggest thanks go to my family, especially to my wife, Jaing, who is an econometrician actually. So we do also talk about science quite a bit, but also about a lot of other things. So for her support and for her understanding of what it's like to be an academic sometimes, and also to our little daughter Vera for all the joy that she brings to my life and for keeping me grounded in reality sometimes. Sometimes that's really important. And at Toronto, I've been very fortunate to work with many very talented and very smart students and postdocs with whom I've really enjoyed learning together and who have also taught me quite a number of things. And some of them will appear in the talk today. I would also like to thank many other great collaborators whom I've encountered since my career. It is probably too many to list here. I think there's too many people who had a very positive influence on me, but I would like to especially thank my advisor, Holger Dette, who kind of caught me just at the right moment when I was about to drift off and start a PhD in pure math, and somehow he managed to convince me that statistics can also be real fun. So without his guidance, I would be somewhere completely else today and probably without a proper job. So thanks, Holger. And of course, I'd also like to thank my colleagues at the department in Toronto. It's a very warm, welcoming, and very nice department. So all of them really make my life so much more enjoyable and so much easier. So thanks to all of them. And especially also big thanks go to Nancy Reed for nominating me for this award, because I know that Nancy is incredibly busy with a lot of things, so the fact that she was able to take out the time for this, I really deeply appreciate it. And the same goes for the letter writers who wrote the letters of support. And finally, I would also like to say a big thanks to Christopher Blier-Wong, who kindly offered me to translate the slides into French on a very short notice shortly before the talk, which really saved me quite a bit of sleep and quite a bit of sanity. So thanks, Chris, for that. Okay, and with that, I'd like to move on to the scientific part of my talk. And what I will do here is I'll first try for the first 20-25 minutes or so to give a brief sort of personal biased introduction to what I think extreme value theory is and why it's kind of important, what the key results and concepts are. I apologize for boring anyone who knows all of this stuff, so you can take a nap for 20 minutes and then I'll try to wake you up when the time comes to look at the things. And okay, so on a very high level, extreme value theory kind of tries to model and understand the tails of random variables. And the reason why we care about tails of random variables is because if you model events through random variables, then the tail of random variables kind of correspond to extreme events. That could be things like extreme floods, that could be things like very high losses on the stock market, and so on. Okay, and so just give you two concrete examples. The first example is a univariate example. So assume that we have 50 or perhaps 100 or whatever, 150 years of data, and those data correspond to flood levels. And the question that we would like to answer is, how tall should we build a dike so that it doesn't get flooded, at least with a very high probability, within the foreseeable future? And this is a question that actually came up in the Netherlands around 1953, because at that time they had a horrible flood that completely overwhelmed all of their flood mitigation systems, put a lot of the country underwater, and actually cost many people their life. So that was exactly the question that they were wondering about at that point. Okay, we have historical data on water levels. How tall should we build our next dike so that we don't get into this situation again? And back then, they were arguably very ambitious. They sort of said, okay, we want to build a dike that doesn't get flooded likely in the next 100,000 years. So you kind of see that how far we want to go in the tail is very far from where we actually have any data. And that's extrapolation, and that's not just extrapolation, that's really extrapolation very far out. Okay, now of course we teach our students that extrapolating beyond the observable data range can be a very dangerous thing. So it's best to avoid it, but sometimes we can't, right? Because we don't have so many data to be able to say something about such extreme events. And then that requires at least some kind of, some models that are justified in a certain sense. And extreme value theory kind of tries to provide that from a more theoretic, thorough point of view. Okay, then as a second possible example, assume that you have a stock or a portfolio of stocks, and then you wonder how large the loss of your stocks and your portfolio will be, conditional on the fact that it's a bad day and you already know that at least one stock in the portfolio had a very large loss. Okay, and that's, of course, important for risk management and for portfolio diversification and for things like that. And in order to answer this question, we really need to understand the dependence structure in the tail. And it's not enough to understand the dependence structure in the bulk of the data, so the dependence structure of what happens daily, because what happens daily might not be informative about what would happen on a really bad day in a really bad economic situation or something like that. And many people say that the last financial crisis was at least partially caused by the fact that people used the wrong dependence model. Okay, some people blame the Gaussian copula for that because Gaussian copulas model dependence in the bulk, but they actually don't have tail dependence. And that's really bad because sometimes extreme events can be much more dependent than events in the bulk. So to summarize this kind of high-level idea in a single picture, what core statistics or most classical statistics would probably do is it would focus on understanding this part of the data. Whereas what extreme value theory does is it tries to understand this part of the data and use this part of the data to say something about what's happening out here. Okay, so that's a very high-level kind of informal summary. And I do apologize, but I couldn't resist putting a couple of beautiful theorems on the slides, so kind of bear with me for that. Okay, so a bit more formally, let's start with univariate extreme. Okay, assume that we have x1 to xn that are IID from some distribution f, and x1 to xn could be things like, for instance, water levels. Okay, then in order to answer some of the questions that I posed on the previous slide, what we really need to do is we need to understand the distribution of the maximum of x1 to xn. So the question that we could pose is what are good models for possible distribution of the maximum of many independent random variables? Again, of course, for any fixed n, that class of distributions is very general. So what we often do in extreme value theory is we kind of take the limit as n goes to infinity and try to see if things stabilize. And there's a beautiful sort of foundational theorem that goes back to Fisher and Tippett, and that was later also worked on by Gnedenko, which goes as follows. Okay, so let's assume that we can normalize our maximum by subtracting something and dividing by something in such a way that it stabilizes or that it converges on distribution to something non-degenerate. If that is the case, if we can find such sequences at all, then the limit must belong to a very specific family of distributions known as a generalized extreme value family of distributions, or short GEV. Okay, so the statement really is, if this converges at all, then the limit must be from this family. Okay, and it's a family that's parameterized by 3 parameters, so mu and sigma are location and scale in the classical statistical sense, so I won't talk about that further. And then there's a parameter psi, which is a shape parameter, and that essentially determines the tail behavior of this distribution, and it's governed by the tails of the original x. And there's 3 cases that all correspond to probably familiar distributions, namely if psi is greater than 0, then we have a Fréchet family of distributions, so those are distributions with power tails, so distributions that have large probabilities of extreme events. If psi is 0, then we have the Gumbel distribution, which many might know from maxima of normals, and then if psi is smaller than 0, then we have the Weibull distribution. And this family of distribution has a nice property called max stability. So if you take an IID sample from this distribution, and all of them have the same parameters, then the maximum also stays within the same family of distributions. Okay, and that's kind of very useful for modeling maxima. So when we want to model maxima of data, a common approach is then to essentially say that, okay, we start with a GV, because if you already have maxima, then this Fisher-Tippett-Gnedenko theorem would sort of justify this modeling choice. Then we estimate the parameters based on the sample of maxima that we have, based on maximum likelihood or M estimators or whatever your preferred choice is. And now we really have a parametric model for the full tail. And parametric models allow us to extrapolate beyond the data range. And that's kind of the whole idea here. OK, now there's one thing that I would really like to mention here, and that is the fact that this convergence here, that's an assumption. So there are distributions that do not satisfy this assumption. It's possible to construct them. Luckily, most textbook distributions that you know, most continuous textbook distributions, do satisfy these assumptions, but it's not always satisfied. Now, the problem, of course, is if this assumption doesn't hold, if the tail never stabilizes, then there's no chance that we can extrapolate to a region where we have no data, because we have no way of knowing what will happen there. So if you have to build a dike, we have to assume something, and I think that's a reasonable assumption, but we should be aware that it's an assumption, not a statement. And the second comment here is that if the data that we have are actually not maxima, so it could be that the data that we have are water levels, let's say daily or weekly, then a common approach is to first block them into longer time intervals, such as months or perhaps even years, take maxima there, and that leads to a class of methods that is known as block maxima methods. And that's essentially kind of a 5-minute summary of univariate extreme value theory, but of course there's a whole literature and the whole community working on this. So this is just a very core, simple ideas. OK, and so that's a univariate case. Now what about the dependent structure, right? Because we might also want to try to understand that. So for the dependent structure, there's a similar style of results that goes as follows. Assume now that we have IID random vectors from some distribution f with continuous marginals of j. Now if the marginals are continuous, then those x have a copula, or have a kind of uniquely defined copula. And then we define the component-wise maxima. Okay, so this is a vector, and the first component of this vector is a maximum of the first entry of xi, the second component is a maximum of the second entry of xi, and so on. So the first component could be the largest stock of loss 1 in a year, the second component the largest loss of stock 2 in a year, and so on. Okay, and then there's, again, a very nice theorem saying that if those copulas converge pointwise to a limiting copula C max, then this limiting copulas must satisfy the following homogeneity property. Okay, so we take each entry of the argument of the copula, which is a d-dimensional vector, we raise it to a positive power t, then that's the same as taking the raising to the power t outside of the copula. Okay, so that's a kind of homogeneity property. And the theorem also says that any copula that satisfies this homogeneity property, which I will call extreme value copula throughout the talk, can arise as a possible limit. Okay, so this is really a complete characterization of all possible dependent structures of maxima. Okay, so those copulas are again max stable in a suitable sense, so they're kind of closed undertaking maxima if you take maxima properly. But in contrast to the univariate case, they form a non-parametric class. Okay, so there's no simple way to parameterize those copulas as a parametric family. But we still get something somewhat less general than fully general copulas, because we kind of lose one dimension, right? So if you look at this homogeneity property, if you know the copula on, for instance, the unit simplex, then you can already compute the values of the copula everywhere. So we have one less dimensional non-parametric class of distributions that we obtain there. And the existence of this limiting copula C max is once again an assumption. Okay, so it's not a statement, it's an assumption. This assumption, for instance, does follow from things like multivariate regular variation, but it is an assumption. Okay, and so that's kind of probably the neat result about block maxima. Now, oftentimes we are interested in dependence in extreme regions rather than modeling copulas. So sometimes it's convenient to use other objects for modeling. And that leads to the so-called class of peak over threshold methods, which I would like to also just briefly mention next in the multivariate case. Okay, so we have the same setting as before, so assume that we have convergence of our copula of the maxima to some copula C max. And now that turns out to be equivalent to the fact that probabilities of exceeding a high threshold stabilize in the following sense. Okay, so for example, let's look at the second formula here. So we take our observations, we standardize them to unit marginals by applying the marginal distribution functions, and then we ask, what is the probability that all of them exceed a marginal 1 minus q times xj quantile? Okay, so if q is really small, then this 1 minus qxj is very close to 1, so it's a really high marginal quantile. And then we ask what happens to probabilities of this sort. Okay, so in the picture, it's a probability of this sort of upper right corner on the copula scale. Okay, now first of all, the first thing to observe is that if you fix the vector x and if you let q tend to 0, then this probability will tend to 0, right? Because even the probability of a single event like this here is just qxj, so that's really small. So if you want to get anything remotely interesting, we have to kind of re-standardize it. So we need to blow it up by at least dividing by 1 over q. And then if you do that, then convergence of the scopula Cn to Cmax actually is equivalent to convergence of probabilities of this type. Okay, and the function R is called tail copula in the extremes community, which is a bit confusing because actually it's not a copula at all. But, well, that's kind of, it sort of summarizes a tail-dependent structure. That's why people probably call it a tail copula. Okay, and similarly, instead of looking at simultaneous exceedances of all our observations, we could ask, what is the probability that at least one observation is large? And that's kind of this probability over here. Okay, and those are kind of the empirical distribution functions and empirical copulas for modeling tail dependence. But sometimes instead of working with copulas, it's more convenient to work with random variables and random vectors, because that's perhaps what we are more used to as statisticians. And it's also possible to do that, and that's also equivalent to the convergence above. So same setting as before, but now assume that we standardize our margins not to uniform, but to Pareto margins. That is just for notational convenience. Essentially, similar types of results hold for uniform margins. Now, if we do that, we could now ask, what is the distribution of our vector of standardized observations if we know that at least one of them is large, right? So this really looks like the Stokes questions that I was asking before. And then one can show that if you condition the distribution of this vector of standardized Paretos, if you multiply it by q and condition on the fact that at least one of them exceeds the marginal 1 minus q quantile, then that converges on distribution to some random variable, and that random variable is typically called multivariate Pareto distribution in extremes. Okay, so it's called multivariate Pareto because certain conditional marginals of it are Pareto. Okay, now this distribution has this kind of funny support where we start with a 0 infinity to the d, but we have to take out the lower left corner. So the support of this distribution is really not a product space anymore. It's this kind of weird rectangle without a rectangle in the lower left corner. And that will create some potential difficulties later. And the notation that I will use for this throughout the talk is x is in the domain of attraction of y, although probably more precisely I should say that the dependent structure of x is in the domain of attraction of y, right? Because we have already standardized the margin. So it's really about the dependent structure at this point. Okay, and if it's more convenient to work with R and L, or if it's more convenient to work with Y, that kind of depends on the setting. So for most of the remaining talk, I will actually work with Y. Okay, now that concludes a kind of brief personal high-level summary of some of the key ideas in extremes. And next, I would like to just briefly mention a couple of challenges in the field. Of course, there's many more, but those are some of the ones that I kind of find particularly pressing and to some of which I have made some contributions. So the first very major challenge is non-stationarity. Right? So because remember, I started my talk by saying, let's assume that our data are IID. Okay, now if you think about something like water levels, and we know that we have climate change, so temperatures are rising, there's more energy in the atmosphere, some ice is melting. The distribution of water levels from 50 or 100 years ago is probably different from the distribution of water levels now. So the data that we have are actually not IID, the data that we have are non-stationary, so the distribution is really changing. And that's a big challenge in EVT, so many people have worked out the classical things under stationarity, but under non-stationarity, some people have started working on it, but in fact, there's not all that much in terms of results. And for instance, Maya Ganem, who has worked with Rafal and with me as postdoc, has done some really interesting work on block maxima methods under non-stationarity. So hopefully there will soon be an archive preprint on that. Okay, then another big challenge in extremes is that in general we have less data that are informative for what we want to do, right? Because remember, the bulk of the data might have one dependence, but the tail might have a different dependence. So we can't really use data from the bulk. We can only use data from the tail, but that means that whatever our sample size is, it will get much smaller once we actually start to try to estimate something. And so it's really important to come up with kind of interpretable and probably sparse, or in some ways simple models that work in high dimensions. And in extremes, high dimensions could be something like 5 or 10, so not high by sort of very classical statistical standards, but still that's already a challenge. And the added challenge here is that most classical models, such as, for instance, multivariate Gaussian distributions that we are familiar with from classical statistics, actually don't work too well in this setting. So we really need to move on to something else. And similarly, a related question is, how do we do inference in the extreme setting? Again, sort of taking into account that we have sample sizes that are typical than our smaller sample and so on. And finally, one other big challenge that I won't really have time to go into today is a challenge of modeling and estimation under partial asymptotic independence. So I'll just mention here that one problem of Gaussian copulas is that no matter how correlated they are, if you go sufficiently far out in the tail, they look like they were from independent observations, at least on the kind of first order. And so really understanding the interplay between asymptotic dependence and independence in higher dimensions is a really big and kind of critical challenge that I think we are just at the start of getting to. And for that reason, I really look forward to the Pierre Robillard talk this afternoon, because I think that we'll talk about exactly things like that. Okay, and so that's kind of a crash course on EVT and current challenges. And for the remaining part of my talk, I would like to say a couple of words about some work that I've done with collaborators, mainly in this area, and I'm almost sure that I won't have time to talk about this area, but who knows. Okay, so, and specifically I would like to talk about a particular class of models that I would consider both interpretable and applicable in higher dimensions, which are graphical models. So what I'm going to present here is joint work with 3 wonderful colleagues, with Sebastian Engelke, who got me interested in this whole direction, with Michaela Lancet, who was my PhD student at University of Toronto, but who graduated and who is now a faculty at UQAM, and with Alexander Ryabchenko, who was an undergrad at U of T and who is just starting his PhD this coming fall. Okay, and I'll sort of credit specific people with specific projects as we go along. So first, let me start with a bit of background on what I mean by graphical models in the non-extreme case, just to kind of bring all of us on the same page. Okay, so if you have a random vector in RD, and if you identify the entries of that vector with nodes in a graph, then a graphical model for X is essentially a graph that encodes certain dependence or density factorization properties of X. And 2 of the most widely known properties are either the global Markov property or density factorization. So the global Markov property essentially goes as follows. Okay, so assume that we have 3 sets of nodes A, B, and C. So for instance, A could be 1. Okay, let's say A is 2, B is 1, and C is 3. Then if A separates B from C in this graph over here, right, which is the case for 2, okay, so 2 separates 1 and 3, because if you remove this from the graph, there's no more connection between 1 and 3. Then we know that x1 and x3 is conditionally independent given x2. And so on, okay? So from this graph over here, we could write down a whole bunch of conditional independence relationships from this kind of separation. So that's one way to sort of summarize and visualize some aspects of multivariate dependence. Another property that's sometimes really useful for simulations and computations and so on is density factorization, right? Because a lot of time when we do statistics, when we apply our methods, we have to sort of compute estimators, or we have to simulate, and for that we have to compute integrals of densities. And in general, computing integrals of d-dimensional functions gets harder and harder as the dimension gets larger, but if you have a graphical model, then it might happen that our density factorizes into lower dimensional functions. Not necessarily lower dimensional densities, but at least lower dimensional functions. Okay, so for instance, in this graph over here, the density would factorize in a function of x1, x2, and a function of x2, x3, x4, okay, because those are the cliques in this graph. And there's a very famous result, the Hammersley-Clifford theorem, which is stating that those two properties and many more properties are equivalent if you have something that has a strictly positive density on a product space. And in the non-extreme world, graphical models are really useful for understanding and visualizing dependent structures, as I was mentioning, for efficient simulation, but also possibly for building predictive models, okay? Because, for instance, here, if you want to predict x1, and we know that we have this graphical model, we also know that we only need to care about x2, because given x2, there's no additional information in x3 and x4. Okay, so this also really tells us which variables are important for understanding which other variables. Okay, now that's in the non-extreme world. And in extremes, things are sort of a similar style, but there's a couple of unexpected small surprises. And the first surprise was that actually if we go back to max stable copulas or extreme value copulas that I introduced as possible limits of dependent structures earlier, then there was a fairly negative result by Yannis Papastatopoulos and Kirsten Strohkorp, which proved that if the copula has a density, then, and if it's max stable, then there's no non-trivial conditional independence relationships in that copula. So more precisely, conditional independence already implies full independence in that case. Not great, right? Because that means we can't really apply our graphical model tools to extreme value copulas. Now, what about multivariate Pareto distributions? Well, the first answer also seems to be negative because actually those are not supported on a product space. And if we have this kind of support, then it's impossible to have conditional independencies. So that also doesn't look good, but luckily there is a way around this, and that way essentially was put forward by Sebastian and later extended with him and collaborators, which is essentially stating that we can define a notion of extremal conditional independence for those multivariate Pareto distributions with the support by first conditioning them to line rectangles, and then sort of doing the usual machinery, but now for all possible rectangles. And they also identified which rectangles are sufficient for that. And then they showed that this notion of extremal conditional independence is kind of the correct notion for multivariate Paretos, because it does lead to all the nice properties that we would like to have, such as density factorizations and interpretation in terms of conditional independence and also other things. And what I would like to focus on in the remaining part of this talk is on the question for how do we actually learn the underlying graph from data. Okay, so assume that we are given a bunch of data and we suspect that they come from some sort of graphical model. Now we'd like to understand their dependence by learning the corresponding graph. And I will discuss two different settings. One is sort of on one side of the spectrum, so we'll talk about very simple graph, arguably the simplest possible graphs, namely trees. But I will be able to say something for completely general multivariate Pareto distributions on those graphs. And later I will sort of go to the other extreme. I will talk about completely general graphs, but only for very special types of distributions. Okay, so what are trees? Trees are essentially fully connected graphs without cycles. So for instance, this guy here is a tree. And if we were to add another edge anywhere here, then it would not be a tree anymore, because then we would create a cycle. Okay, right? So a brief summary of the first results that I would like to present is up here. So trees for extremal graphical models can be identified from simple summary statistics that essentially involve moments. So if you go back to the definition of graphical models that I was giving earlier, one might think, okay, to learn the graph, you now need to test a lot of conditional independence assumptions, or we need to estimate a high-dimensional density and look at its factorization, but luckily it turns out that we don't have to do any of that if we want to learn trees. Okay, now a bit more specifically, assume that we have a multivariate Pareto distribution Y, then we can define a certain summary statistic for the dependence between two components of that multivariate Pareto distribution. Okay, now it doesn't really matter what the precise form of this is. I think the important message is really There's a variance, so it's based on moments, and inside we just have a simple logarithmic transformations of a certain vector that we can define from y by simple conditioning. Okay, so you can already sort of see that if you had observations from y, then it shouldn't be too hard to write down a reasonable estimator for this quantity. Okay, and now why is this an interesting kind of summary of the dependent structure? Well, the reason for that is the following result, which is due to Sebastian and me, which essentially has the following two parts of the statement. So first of all, if we assume that y is a multivariate Pareto distribution on a tree, and if there exists one M for which all those summaries of dependence are not zero and not infinity, which means that the entries of our y are not perfectly dependent and not perfectly independent, and that they don't put too much mass near the axis, then if y is a graphical model on this tree, then the tree T is actually the unique minimal spanning tree. Okay, now what does this mean more precisely? So imagine that you have distances rho ij that you put between any two nodes I and j. Okay, so between any two nodes you can define a distance. Now the minimal spanning tree is the one tree that minimizes the sum of distances while connecting all of the nodes in our graph. Okay, and of course the minimal spanning tree doesn't always need to be unique, but it turns out that for this type of multivariate Pareto distributions, under this assumption, the minimal spanning tree is actually unique. Okay, so that means that by knowing those kind of those moment-based summary statistics, we can identify the tree without any kind of conditional independence testing or anything of that sort. Okay, so that's a really nice result because that also allows us now to have some ideas about how we would estimate those guys. Now that's what I would like to talk about next. But before I go there, I would also like to mention that there's a very nice stochastic representation for the random vector y over the tree, which I have on the backup slide. So if there's a bit of time in the discussion afterwards, if anybody would like to see that, then I'll be happy to comment more on that. Essentially what this stochastic representation implies is that it's very easy to simulate from multivariate Paretos on trees, even if those trees are fairly large. So it's easy to simulate from this type of distribution, even in fairly high dimensions. And another thing that I would like to mention here is that in the non-extreme world, there actually do exist similar types of results, but they're not quite as neat because what we would need to put as distances on the edges of the graph is actually something that is called mutual information. And that is in general much harder to estimate because it involves densities and smoothing and kind of other things. Okay, so in the non-extreme world, similar results exist, but the summary statistics that we need to consider are much more complicated than the summary statistics that we need to consider here. Okay, right, so that's the kind of probabilistic foundations of all of this, and now I guess all the statisticians in the room can already guess how we could leverage this result for estimation. Now, there's one kind of slight complication here, and that is the fact that in reality, the sample that we have is actually not from y. Right, so we want to say something about y, but we don't observe data from y. We only observe data from x, whose tails is approximately similar to y. So in our estimation procedure, we need to take that into account. And we would do that by two steps. First of all, recall that only the dependent structure of x is in the domain of attraction of y, so we standardize our margins by the empirical CDFs. Now, I don't think that will shock anybody in Canada. That probably has the largest per capita proportion of copula experts anywhere in the world, so we kind of know how to deal with that. Okay, and the other thing that we need to take into account is that we are only in the domain of attraction of y, so that means that we should only use a subset of our sample that is kind of informative about the tails. And that essentially informs the shape of this estimator. So you can sort of ignore the first part. It's just important that this can be computed easily from the data. And the part that I would like to spend a bit more time on is explaining this piece over here. Okay, so FM hat is the empirical marginal CDF of XM. We evaluate that at XTM, and then we ask that this is larger than 1 minus k over n. Okay, now this k here, that's a tuning parameter of our estimation problem. And this is essentially saying that we only consider vectors where the m's component is among the k largest. And hopefully that will kind of bring us close to the tail of our distribution. Now, of course, the first question that anybody would ask seeing this is, how do you choose this k? And unfortunately, that is probably one of the hardest foundational questions in extreme value theory, which hasn't been answered since the beginning of EVT and which is kind of doesn't really have a universal good answer. Now, perhaps I'm oversimplifying things a bit here. Of course, it does have answers. For instance, if you want to minimize the mean squared error of your estimator, then you can write down a second order condition that controls the bias, and you can derive an optimal choice of k. So all of that exists. But what a good choice of k is could be very different in theory, where you have optimal mean squared errors, and in practice, where you actually want to work with data. So that's kind of a really tough question. And in a sense, it's even tougher than bandwidth choice, because for choosing a bandwidth and kernel density smoothing, we at least have cross-validation. And in EVT, we actually don't have cross-validation for choosing k because we have no observations from y. So that's kind of one of the challenges here. Just mentioning that, but I'm not going here. This problem is too hard for me. So I will kind of assume that we can choose k suitably and then go from there. Okay, but given that, the form of this estimator, I think, would be very intuitive if we had time to look at the previous formula again and sort of look at this formula. It's essentially a plug-in approach that replaces q, little q, that we had in the limit of the domain of attraction condition by k over n. Okay, now given this estimator, what can we say about the probability of recovering the correct tree? Okay, so assume again that we have a multivariate Pareto distribution on a tree, that we have IID samples from X, which is in the domain of attraction of Y. And in order to describe the main result, I essentially need two things. First of all, if you put a condition on the speed of convergence in this domain of attraction condition, then we can characterize the bias that our estimator gamma hat would have for gamma. And this bias would really be due to the fact that X doesn't exactly follow the distribution of Y. And the second crucial ingredient for this theorem is essentially a lower bound on the minimal separation between the minimal spanning tree and the second minimal spanning tree. Okay, so imagine that I could construct two trees, and the sum of distances on those trees, I can lower bound for any minimal spanning tree and any other tree by this kind of quantity here. Now, of course, it's reasonable that that sort of determines how hard our problem is, because if the minimal spanning tree and the second minimal spanning tree are very close by, and I estimate all the weights with some errors, and it's really easy to confuse those two trees. Okay, so in order to be able to identify my tree from noisy observations, I of course need some separation between the best tree and the second best tree. And that's essentially what this quantity here is quantifying. Okay, it's not immediately obvious from the definition, but it follows from some specific properties of multivariate Paretos on trees. Okay, now assuming those two conditions and assuming some mild assumptions on Y, which essentially prevents it from putting too much mass near the axis or becoming too asymptotically independent, we have an upper bound on the probability that we recover the correct tree. And that is essentially upper bound by something that's a constant times dimension cube, which seems bad, but also times e to the minus constant times k times something, which is good because k is our kind of sample size, and e to the minus c times k decays very rapidly as k gets large. Okay, so there's hope that this term over here decays very rapidly, and the c times k is multiplied by two things. First of all, some kind of distance between the minimal separation of our trees and the bias. So if the bias dominates the minimal separation, we have no chance. But if the bias doesn't dominate the minimal separation, then this guy here is positive, so we can treat it as a constant. And then there's a minimum with another term that kind of comes from certain concentration inequalities and tails, and I don't really want to go into too much detail here. Okay, but essentially this does go to 0, but it does go to 0 polylogarithmically in n, so asymptotically k will be much larger than that. Okay, and then we have an upper bound for the correct recovery of our tree. Now, if you digest this theorem in two special cases, first of all, if the dimension d is fixed, and if k grows not too slowly with n, then it's actually sufficient that k over n goes to some q that is sufficiently small, and then we get correct recovery of the tree. If conversely, let's say for simplicity, we fix a minimal separation, but we let the dimension grow, then the dimension can grow as quickly as k over log n to the 8. Okay, so the dimension, sorry, not the other way. So the log of the dimension can grow as quickly as k over log n to the 8, which means that the dimension can grow almost exponentially, and we still can recover the correct tree. So at least in theory, we can estimate even trees that are fairly large with a relatively limited sample size. And the crucial ingredient for proving this theorem were actually concentration bounds for gamma hat minus gamma, which were part of Mikhail Lancet's PhD thesis. All right, now, Now, given all of that, I would like to briefly provide data illustration to sort of show that although trees are relatively simple graphs, they still possibly contain some interesting structures that we can extract from our data. So what we did here is we looked at we looked at currency exchange rates of all possible currencies to the British pound sterling between October 2005 and September 2020. So that's about 3,800 observations. Then we considered daily log changes for each currency. So we really consider sort of day-to-day changes. And then we decorrelated them by using an Armagard filter. That was a type of pre-processing that also was done by other people previously on this data set. So essentially, that's kind of decorrelating. And then we estimated the minimal spanning tree from the corresponding filter data. And this is the tree that we obtained. Okay, now there's a couple of sort of interesting things here. For instance, if you look closely, then you'll see that most of the European countries' currencies are very close together. Okay, so here's the euro, here's the Swedish currency, the Norwegian currency, the Danish currency. Okay, so the kind of the northern countries cluster closely together, the Eastern European countries cluster closely together. Then similarly, we have a bigger cluster of countries that are sort of the Far East and Asia. They also are close together. We have countries from the former Commonwealth that are around here. And then one interesting thing here that sort of caught our attention is that for some reason, Japan is connected to Switzerland. And to us, it didn't make too much sense initially. But then it was explained to us by experts on banking that actually both the Japanese currency and the Swiss currency are considered as kind of safe haven currencies. So if the economy globally isn't doing well, if you're in a time of crisis, and people tend to run to those two currencies to sort of save their money. So actually this connection down here also makes a lot of sense, and it's much stronger in the tail than it is kind of in day-to-day. So if you would look at the bulk of the data, for instance, you would not see this connection. Okay, so this does extract some useful information from the data that we can interpret. That's a good sign. Now, we also tried to see how stable this tree is under small perturbations of the data. So we did the same filtering, but then we repeatedly bootstrapped our sample. And we re-estimated the tree every time. And then we sort of saw how often each link is selected for each of the bootstrap samples. And the thicker the lines here, the more often the link is selected. And you see that a lot of the structure that I was describing is interpretable is actually fairly stable. So for instance, this link between Japan and Switzerland is fairly stable under small data perturbations. The kind of cluster of European countries and the cluster of Asian countries is relatively stable. But there are also connections that seem kind of random and stochastic. For instance, the connection of Russia's currency to most of the other currencies is kind of really depends on the samples that we get. Okay, so the connection of Russia to anything in here I wouldn't really overinterpret. Okay, and that concludes my discussion of trees. Now for the last part of this talk, I would like to talk about the sort of the opposite, namely general graphs for very specific distributions, and most specifically for so-called Huesler-Rice distributions. Okay, so Huesler-Rice distributions are a particular parametric class of multivariate Pareto distributions. And they are parameterized by something that's called the Huesler-Rice precision matrix, which actually is very similar to a Gaussian precision matrix, but it does have some additional structure. Okay, so it is a D by D matrix. It's symmetric. It's positive semi-definite. However, it's not full rank. It is rank deficient, so it has rank exactly D minus 1. And the rank deficiency is due to row sums 0. Okay, so you could use this as a very particular type of correlation matrix with a certain additional structure. Okay, and then given this Huesler-Rice precision matrix, we can, for instance, write down an explicit formula for the density of the Huesler-Rice distribution, which looks like this. Okay, now, one thing to note here is that this part with the exponential looks very much like a Gaussian density. Okay, so we have, with the exception that instead of y, we have log y. And instead of a free parameter mu, we actually have a parameter mu theta that now completely is characterized by this theta. Okay, so we don't have a free location parameter and a free scale parameter. Those two parameters are linked together for this type of distribution. And then there's a bunch of other things really showing that it's not quite a Gaussian, but at least part of the structure of the density looks like it is related to a Gaussian. Okay, the reason why this is a popular class of distribution in extremes is that, first of all, because it's closed under taking marginals after proper conditioning. That's a nice property. Right, so if you start with a high-dimensional Huesler-Rice, we take a subvectors, and that corresponds to Huesler-Rice again. They also correspond to finite-dimensional distributions of so-called Brown-Resnick processes, which are popular max-stable processes used in spatial extremes. And finally, they are the only continuous multivariate Pareto distributions that forms a pairwise interaction model. Okay, and the pairwise interaction model is essentially a model for a density where the density has a particular structure. Okay, and it was proved by Mikhail in 2024 that this is really the only multivariate Pareto distribution that has this property. And this is a well-known property in graphical modeling, so it's a very kind of convenient and useful property. And the final reason why I'm introducing this distribution here is because it has a very nice probabilistic interpretation. Okay, so if you look at the sparsity in the matrix theta, and if we write down a corresponding graph where we put edges where we have non-zero entries and we don't put edges where we have zeros in the entries of the precision matrix, then one can show that if y is a Huesler-Rice with this precision matrix, then it's also an extremal graphical model on this graph. And this now really looks exactly like Gaussian graphical models, right? Because in the Gaussian world, the precision matrix characterizes conditional independencies. It turns out that for Huesler-Rice distribution, we have the same case. Okay, and that also gives us a path forward to actually estimating this graph, because now the hope would be that we would estimate the precision matrix, and then based on that, we could estimate the graph. Okay, now similar to the precision matrix in the Gaussian case, the entries of this precision matrix theta actually are not simple moments of our distribution. So it's impossible to just write down moment-based estimators and then directly use something like thresholding. Rather, we can show that the theta is the Moore-Penrose pseudo-inverse of a matrix sigma, which we can compute from the matrix gamma that I've kind of introduced before as a summary of certain dependence structures. Okay, so this matrix gamma we can really estimate based on moments of our data. Then we can transform it into sigma by a known transformation. And then if we take the Moore-Penrose pseudo-inverse, we arrive at theta. Okay, so this kind of looks again like Gaussian graphical models, but note that here we have a pseudo-inverse and not a proper inverse. And that kind of complicates things quite a bit. Now there's two possible solutions to this, and the first solution is a solution that we explored with Sebastian and with Mikhail in Mikhail's thesis, which essentially goes as follows. Okay, let's assume that we fix an m. We take our theta, but now we remove the mth row and column. If we do that, then one can show that this matrix actually becomes full rank, so it is invertible. And its inverse is a matrix sigma superscript m, which we can construct from sigma. It's not the matrix sigma with the mth row and column removed, but there's a simple explicit formula for going from sigma to sigma m. Okay, so we could use this information here to estimate the zeros in theta with the mth row and column removed. Now, of course, that doesn't give us the information of the full graph, because removing the mth row and column is the same as removing the mth node from the graph. But we can repeat this procedure for every m, and then we can aggregate the estimated subgraphs to a full graph by some kind of majority voting, for example. And that's exactly what we proposed in this paper with Mikhail and with Sebastian. Okay, then in there also was a proof for how well we can estimate sigma by sigma hat in element-wise soup norm. And again, the good news here is that, okay, the bad news is there's a bias term, but the good news is that dimension only enters as a square root of log d, so this is still a good estimator in element-wise soup norm, even if the dimension is fairly high. And then we sort of use this majority voting idea to provide theoretical guarantees on the probability that we recover the true underlying sparsity of theta. Now, I don't want to spend much more time talking about this, because it's done, and I would rather like to sort of talk about something else that we are kind of wrapping up right now. And the reason why I want to go there, so what's the problem with this approach? Where essentially it does provide an estimator of the graph, but we might also want to have an estimator of the theta, that is a valid Husserl-Rice precision matrix. So ideally, we would like to have both the estimated graph, but also the full parameter matrix for simulation, for statistical inference, and so on. Okay, but this doesn't provide an estimator of theta. It only provides an estimator of submatrices of theta, but it's not clear how to combine them together. So instead of estimating a bunch of matrices and gluing them together, why don't we try to estimate theta directly? And the first thing that we tried that looked reasonable to us at that point in time is the following. Okay, so first of all, because we know exactly in which way theta is rank deficient, we know how to make it not rank deficient. Okay, essentially the kernel of theta are the sort of the constant vectors. So if we add a matrix, for instance, the matrix of 1s divided by d that doesn't have 0 in its kernel, then this matrix now becomes full rank. Okay, right? And because this matrix becomes full rank, one can then show that if we take the sum, then we can compute the inverse. And what we get is essentially a nice formula for theta through a proper inverse. Okay, now first idea would have been we plug in sigma hat that satisfies this kind of zero row sum constraint. Then we could obtain a theta hat like that, but that theta hat would, of course, first of all, not be sparse, and second of all, the sigma hat might not have full rank. Okay, so what people do instead in the Gaussian world is the so-called Gaussian graphical lasso, which essentially in the Gaussian world would be this optimization problem here, except that we would optimize over all positive definite matrices without the zero row sum constraint. We would remove this piece over here, but otherwise this looks exactly like the Gaussian graphical lasso. Okay, and that's known to work in the Gaussian world. And we saw that, okay, we only make some very innocent changes. Okay, we adjust here a bit, and we restrict the search space a bit, so what can possibly go wrong? And then we started simulating. The slides kind of stopped moving. Okay. And what we saw is that we actually never were able to recover the correct graph. So here's a simple example. We have a tree in dimension 10. I simulated data from the exact Husserl-Rice distribution with 10 to the 5 observations. That's like a huge sample size for extreme. And then we looked at the number of edges in our estimated graph against the number of edges in our true graph. And no matter how we choose a parameter, we never get even close to the correct number of edges. And the other thing that should look surprising here is that as we keep increasing the penalty parameter over here, the graph doesn't get sparser, it gets denser. Which kind of doesn't make sense, right? Because if we add more penalties, the graph shouldn't be getting denser. And the reason for this is exactly this kind of zero row sum constraints, which kind of breaks the whole geometry. So we were later also able to show that this is not just a random feature of this particular data set that we simulated, but that as a matter of fact, it is a theoretical a property that we can characterize theoretically. Okay, so assume that we have an estimator for sigma that is, in a suitable sense, multivariate normal asymptotically. Then define a certain parameter which is kind of akin to the incoherence parameter in Gaussian graphical models, but looks slightly different. So don't look at this formula too long. It's still early morning. It doesn't really matter, but it should kind of look a bit like the incoherence parameter in Gaussian graphical models for people who have seen that. And then we were able to prove that if this incoherence parameter is strictly greater than 1, then asymptotically the probability that we recover the correct support is bounded by 1/2, essentially no matter how we choose our penalty sequence. Okay, so this is a really strong negative result. It is essentially saying that the graphical lasso idea really doesn't work. And we were also able to prove that if our graph is a tree, then this incoherence parameter is the diameter of a tree, which means that it is at least 2 for any tree that's not completely trivial. Okay, so this really shows that we have no hope of estimating trees using this naive idea. But in certain situations, and in extensive simulations, we've never seen a graph where this actually worked. So the strong conjecture is this never works. And that's kind of in stark contrast to the Gaussian world, where we do need incoherence parameters to be small for supports recovery, but there are plenty of examples where those incoherence parameters actually are small. Okay, so what do we do about that? Again, we can sort of learn from the non-extreme world. And one of the things that people do there to avoid incoherence conditions is to add weights into the penalty. Okay, so that's also what we propose to do here. So essentially the idea is here that instead of doing a non-weighted penalty, we sort of do a weighting from a preliminary estimator that adjusts to the specific structure of our problem. And if we do that, then ta-da, things work. Okay, so things get sparser, and we also estimate the correct graph. Now, you have the correct sparsity, and we actually do estimate the correct graph. Okay, so for the final slide here, I would just like to show that we do have theoretical results showing that this works, and essentially the theory goes like this. So assume that we compute our theta hat with some input sigma hat from weights W that satisfy 2 conditions. Okay, so the PR sigma hat and the weights need to satisfy 2 conditions. Okay, first of all, the maximal error in estimating sigma combined with the maximal penalty that we put on non-zero weights has to be bounded from above by 1 divided by the largest node degree of the graph times an ugly constant c that depends on theta but not explicitly on the dimension. And second, the smallest number of penalties that we put on zeros should be greater than the noise in estimating sigma plus the incoherence parameter times the largest penalty that we put on the zero patterns. Okay, now we show that those 2 conditions can be satisfied by the estimator sigma hat computed from gamma that I showed you before. For instance, if we use the climb approach for estimating those weights, so we do have theory examples where this condition is satisfied, and then we have a sort of non-stochastic version saying that if those conditions are satisfied, then deterministically, we will recover the true support under a minimal signal strength assumption. And we also do have a convergence rate for element-wise subnorm estimators of theta. Okay, so combining that with tail bounds for sigma hat minus sigma, we can then obtain theorems like I was showing before on probability bounds on recovering the correct graph. Okay, now with that, okay, slide, yeah. I would just briefly like to mention some ongoing and future work. So the first big question that we are looking at right now is inference. Okay, so far I've told you how we estimate the graph. I've given you sort of convergence rates. But of course, as statisticians, we would like to have tests and confidence intervals. And that's something that we are currently working on. In particular with Yeonjun Choi, who is my PhD student at University of Toronto, and with Axel Bücher from Bochum and Katharina Efferts, who is his PhD student. And as a first step sort of in this direction, what we needed to do is we needed to derive some sort of CLT-like or high-dimensional CLT for estimated parameter matrices in growing dimensions. That didn't really exist before, so that was kind of the first step that we did, and we already had to write a small novel to kind of to prove all of this, but that's kind of the first thing. And then one of the many things that I would like to consider in the future is to study directed graphs in extremes and link that to a notion of causality. Now, one thing in extremes and causality is that it's not even completely clear how we would actually define causality in extremes, right? Because we kind of have a couple of causality definitions in the non-extreme world, even there's a big philosophical debate about which one we should choose. But as we go to extremes, we might not be interested in all types of causality. For instance, we might only be interested in types of causality where the question is which intervention can actually change the tail of our distribution. And how exactly one would describe that, that's, I think, a very interesting question that people are starting to work on. But that's very largely open. Okay, so with that, I would like to give a big thank you to the audience for both for showing up so early in the morning, despite the nice banquet yesterday, and also for staying awake and not kind of snoring during my talk. So thanks a lot.
Stanislav Volgushev. So I'm not that familiar with the extreme value series, but this is sort of a more general question. But when you're extrapolating way out into the tails, way beyond any data that you've observed, is it fair to say that the conclusions you might reach way out in the tails could be very sensitive to the fit, right? And like if, say, one data point is a tiny bit different, it could really lead to a very different conclusion way out in the tails. So can you comment a little more on that in terms of the stability of these extrapolations that you make by these theories?
Yeah, so that is really kind of one of the big problems with any kind of extrapolation. And yeah, when you say that you sort of, if you change one observation a bit, that could have a big impact, that's kind of part of what is a difficulty in extreme values theory. Because if you move one observation further to the tail, that would very strongly change our perception of how likely is it that we have a very large observation in the tail. So yeah, that is a problem. Now, if you're worried about data quality, you should be very careful about that. And there are methods that are sort of called robust extremes, which try to find outliers in the tail in a certain sense, although that's a kind of a hard to define concept. But I would say if you have most of your observations are from a well-defined tail, and then one of them is completely off, you would do sensitivity analysis, you would include that observation, you would exclude that observation, you would kind of see how much things change, and then you would really need to decide in the end if that observation is a true observation or if that's an outlier. So there are kind of principled ways of doing that, but in general, it's an even harder problem in extremes. So we can't just throw away whatever. We can't do a trimmed extremes or something like that. It doesn't really make sense.
So that's about the data, but what about like, say, the modeling, like with a slightly different functional form of the model or something, you can also get very different prediction output. Yeah.
Oh, so you mean when you change your estimator?
Well, yeah, anything that you change could make it really different. Right?
Well, yeah. So in general, if you kind of look at, for instance, confidence intervals that are constructed from this extrapolation, then typically, of course, the further out in the tail you go, the wider they will get. And that is really unavoidable. But in general, I would say that those things are kind of reasonably stable if you stay away from problematic regions. For instance, this transition from psi greater 0, which corresponds to polynomial tails, to psi equals 0, to xi smaller 0, that's a really problematic one. So if xi gets close to 0, then that gets hard, because you get a very different extrapolation far out in the tail. If xi is slightly positive, then it's a polynomial tail. If xi is slightly negative, then it's a much lighter tail. So there, depending on the application, I would kind of err on the side of caution. I would probably not construct symmetric confidence intervals, but kind of go to one side. But that's actually one of the big problems. Now, that said, in some kinds of data, like I think in, there are examples where xi is actually sufficiently non-zero for not causing big problems. But yeah, in some applications, that's difficult.
This is very impressive research. My question's on how does the graphical structure change if you start adding and deleting variables? So the particular one, if you have a sparse Hussler-Rice precision matrix, what happens if you start, do you still keep this sparsity if you delete or add variables?
Yes, so I'm reasonably sure that if you start with a high-dimensional Hussler-Rice, and okay, so your question is, let me first start with that. So your question is, you start with a Hussler-Rice distribution, then you remove a couple of nodes, and then the question is, how does the graphical structure change? I'm fairly sure that what would happen is that essentially you would remove the corresponding rows and columns from your precision matrix, right? It would get smaller. You could write down a graph for that one. And then the conditional dependent structure of the subvector would now be encoded by that graph. I think that that's what should happen. So essentially, you remove a couple of rows and columns, you get a smaller matrix that has a certain sparsity pattern. You look at the graph corresponding to that sparsity pattern, and that's now the correct graph for this subvector. With one small caveat, and that's if you just take your multivariate Pareto and you remove a couple of entries, then it's not a multivariate Pareto anymore without proper conditioning, because you kind of break this support. So if you remove entries, you have to kind of recondition it to be on the right support. But if you do that, then you would get the right thing. Or speaking in terms of density factorizations, actually that would sort of carry over without problems.
Thanks for the talk. That was very interesting. I think I learned something about characterizations of various things of what extreme values from it. What I wanted to just ask for a comment on was extremes occur in time, and processes are inherently dynamic.
Mm-hmm.
And time is implicit in a lot of what you said.
Mm-hmm.
Sometimes, like with peaks over threshold models, it's a bit more explicit, but I'm really curious as to if we think about predicting extremes in a dynamic situation, do you have any comments on how this applies to that, or whether it could be modified to deal with that sort of thing?
Yeah, that's a great question. And actually, some of the simple links that I was discussing kind of start to change once we have data that change over time. So for instance, in the univariate case, if you have a time series, then depending on the dependent structure of the time series, if you look at peak over threshold versus block maxima, we might get different estimators. And I think in the univariate case, there's a lot of work on declustering and sort of removing this clustering behavior in extremes that we often get for dependent processes. In the multivariate case, I think, to be honest, there's somewhat less. And in particular, the answers, the dependent structure that we get from peak over threshold, whereas the dependent structure that we get from block maxima can really start to diverge. So I don't know of a kind of universal answer to what one would do about that. And I think there's also now, in a sense, there's two distinct questions. Right? So I think one question is if you want to really forecast what is the probability that you have a large flat in the next, whatever, 500 years of at least this size, then you do need to take into account that water levels are dependent, so you will have this dependence. If you just want to ask the question, what is the probability that on a given day a flood exceeds a certain level? That's more of a marginal question that is actually, there the dependence in the time series is not as relevant. So I'd say it also really depends on what type of question you're trying to answer, how careful one would need to be about the dependence. But this is really a great point, and I don't think that there's anything really systematic on those kind of graphical models or on this type of model in a sort of more temporally dependent context. Thanks.
Do you have any further questions?
Does any notion of dependence extend into space? Like if you had probability of flood along a coastline, you've got a spatial configuration to where you're sampling things from. Does this dependence work spatially?
Yeah, so there is also some work on that. There is, for instance, foundational work on what type of processes you could get if you take spatial processes and you take their maxima, and then you kind of try to characterize what the limiting process is if you properly normalize that maxima of spatial processes and kind of look at the limit. And that, for example, leads to things like those max stable processes if you look at maxima, and there's also sort of versions of threshold exceedance processes for doing that. I would say that one challenge that people have been facing there is that what we often observe in data is that the more you go into the extreme tail with certain types of data, the more localized the dependence becomes. So for instance, if you look at extreme precipitation, kind of extreme precipitation at a certain level of extremeness can probably occur in a wide spatial domain because of a big storm. But if you really start to zoom into the very tails, then it becomes more and more localized because a really, really heavy rain sometimes often is very local from kind of local clouds. And so that is kind of going into this asymptotic dependence versus asymptotic independence direction and all of that I think is a very interesting and very challenging question. So people have tried to model that. People have tried to come up, for instance, with spatial models that allow for asymptotic independence at further away locations and for asymptotic dependence sort of at closer locations. But I don't think there's like a definitive answer to that so far. But yeah, that's a very interesting.
From the graphs you know, I was wondering if you could have spatial locations and figure out the dependence, a graph dependence among them, and then it might have some structure for like ocean flow, like floods in one area associated with floods in another area kind of thing, where it's discovered from data rather than explicitly spatial.
I'm sorry, I think I only caught half of what you were saying.
With the graph models that you have, dependence on a graph, if you had spatial locations that were along a coastline and maybe spread widely across the ocean, maybe dependence among the extremes might not be beside each other, they might be across the ocean because, say, ocean currents affect one and the other.
Yeah, so that, there actually those graphical models could be very helpful because if you sort of just look at it as a graph and first ignore the spatial information, then you might be able to discover things that are not spatially close, but close through some other physical processes. Yeah, that's a great point.
All right, so maybe I can ask one more question. So I was wondering about the multivariate extreme concept itself. So maybe from my understanding, you're doing this like for each dimension you have extreme, and then you model those extremes together, right? So how about is there a possible way to consider something like a contours, like this kind of not just marginal extremes, but like some kind of not abnormal behavior or like extreme behavior jointly in the high dimensions instead of just marginally together.
Well, so in some ways, I think there might be, I mean, there has been some works on
Like this data depth type of stuff. Like
Yeah, exactly. So there has been some work on trying to sort of link extreme value theory and, for instance, those multivariate quanta, like Tukey half-space depths or kind of related things. Yeah, there has been some work on that. I think the challenge really is if you want to sort of look at all directions simultaneously, right? Because if you fix one direction, you could project your data in that direction, and then it becomes a univariate problem again. But if you really want to look at the sort of full sort of multivariate quantile sort of settings, then I think, yeah, things do become more challenging. I'm sure that somebody has tried to look at that through the lens of optimal transport. I think I saw a paper of that form as well. I don't think that there's any very definitive conclusions there at this point, but it definitely would be a very interesting thing. So I mean, you could even ask that question in the not as extreme world, right? If you go from copulas to some sort of more geometric notion of what happens. There's actually also a whole area called geometric extremes, where people sort of, what people do is they standardize their margins and on, for instance, exponential scale, and then they look at the shape of the point clouds that you get in the tail. And then, for instance, one can show that if you get point clouds that are kind of, that have corners, that says something about asymptotic dependence versus asymptotic independence, whereas if they're round, then you have asymptotic independence. If they have corners, you have asymptotic dependence, and so on. And then people try to just model this kind of geometric shapes that you can get for those point clouds. So that could also go sort of in the direction of your question. And yeah, one advantage of that is that there's the distinction between asymptotic dependence and asymptotic independence is not as strict there, because there it's kind of really determined by the shape of that point cloud. Yeah.
Great, I think we can finish today's this session, and thank you everybody for coming.